Hello everyone, this is Mr. Beckstrom, and today we're going to be talking about section 5.6. This is solving exponential and logarithmic equations. Like always, you can find this PowerPoint file in the Canvas site under Files. All right, let's go ahead and get started. This is solving exponential logarithmic equations, like we just said. So solving when both logarithms are the same. So if you remember back to when we talked about exponential equations, if we had the same base on each side, then we could set the exponents equal to each other. Well, we can do a very similar thing with logarithms. So if we have two of the same logs, again, we don't have any factors out in front, and we just have the logs by themselves on both sides of the equal sign. If they're the same base, then we can let the arguments equal each other. So in this case, x would equal to y. And again, very similar to the exponential equations from section 5.5 that we just covered. All right, so let's take a look at an example of how we might use that. Well, let's say I had log base 5 of 2x plus 3 is equal to log base 5 of x plus 8. Notice that the logs are by themselves on both sides, so we're not adding or subtracting anything. There's no factors out front like a 2 or 3 or -7. So these we're ready to use the rule that we're just looking at here, where these arguments have to be equal. So we can just set those arguments equal to each other and then solve for x. So 2x plus 3 is equal to x plus 8. If we subtract x from both sides, we'll get x plus 3 is equal to 8. Subtract 3 from both sides, and we should get x is equal to 5. Now, the next thing we want to do, because we have a domain of logarithms of strictly positive numbers, we want to put that x back in and make sure that our argument stays positive. Well, if I put a 5 into here, I'm going to get 2 times 5, which is 10 plus 3, which is 13. Well, that's fine. So 5 works there. But I also have to check this one. So 5 plus 8 is also 13. Thus, it is positive. The argument is positive for all logarithms involved. So 5 would be our solution. All right. So now we're going to rewrite as an exponential equivalent, and we're going to take a look at how to solve that. So here I have the log of x plus 85 in the argument is equal to 2. So if we recall, if we do not see a base here for log, that it's assumed to be 10. So if you want to write a little 10 in the lower right of the log at this point, you can if it makes it a little bit easy for you. And then as we learned to go from logarithmic to exponential form, we can take that base, raise it to the power that's equal to the other side of the equality, and set that equal to the argument. So this should be 10 raised to the second power is going to be equal to x plus 5. So 10 squared is equal to x plus 5. Now we just have a pretty simple equation. Subtract 85 from both sides. 10 squared is 100, so 100 minus 85 is equal to 15. Again, we're going to put that 15 back in the argument, make sure that we get a strictly positive number. Now, don't forget, when I say strictly positive, I mean we can't get a 0 and we can't get a negative. It has to be strictly greater than 0. All right, so let's use some of these properties that we learned from the last section in order to rewrite as a single log. And then we can use that formula to change from the logarithmic to the exponential form. Right, so here we have log base 4 of x plus log base 4 of x minus 3 is equal to 1. All right, so as we might notice, we have the same base for both the logs, and we're adding those two logs together. What does that mean? Well, that means that we can combine it under one log where we multiply the two arguments together. So remember from the logarithmic rules, section 5.5, that we can, if it's the same base and we're adding, we can combine into one log under multiplication. And if we're subtracting, then we can combine under one log under division, so long as the second log's argument is not equal to, or not the argument, but the entire log is not equal to 0. All right. So we're combining these under one multiplying the x times the x minus 3. Don't forget to distribute that x. Sometimes if you just write it out, you might think you just have to multiply the x by the x, but we also have to multiply that x by the minus 3. So that'll give us log base 4 of x squared minus 3x is equal to 1. Now remember, we're going to use that base change, not the base change, but the logarithm to exponential formula. So I'm going to take the base here, which is 4, raise that to the first power, and set it equal to the argument of x squared minus 3x. So 4 to the first power is equal to x squared minus 3x. Now we just have a quadratic to solve. I can subtract the 4 from both sides. I flipped around the equal sign and the quadratic here. So this is just a factoring problem now. So we were looking for, again, two numbers that multiply together to give us a negative 4 and to add together to give us a negative 3. So that would be negative 4 and positive 1. So we can set it up like this. Set each one of those equal to 0, and we have 4 and we have negative 1. Now, you might think that this is the correct answer, but again, we have to take these values and put them back in the original equation and check to make sure that those arguments are positive. Well, starting with the 4, if I put log base 4 of 4, well, that's an argument of 4, so that's good. And 4 minus 3 is 1. 1 is positive, so that's good. If I do the negative 1, I'll get a negative 1 here, which we can't do, so that already eliminates the negative 1. But I can also see that it eliminates it for this reason as well, because negative 1 minus 3 is negative 4, which we can't have a negative in the argument. So our solution here would just be x is equal to 4. All right. Here's another one. So I want you to pause the video at this point, and I want you to give this a try on your own. We're going to combine it into one logarithmic equation, and then we're going to use the logarithmic to exponential formula to change that and solve. All right, so hopefully you've given it a try. So we might notice that we can only combine these logs under division if and only if there's no factors out front. Well, here we have a factor of 2 out front. So what can we do with that? Well, remember from, again, section 5.5, that if we have a factor, we can move it up to the exponent position and vice versa, right? As long as it's a logarithm. So I'm going to take this 2 and I'm going to put it up into the exponent position, and that will then give me a log base 3 minus a log base 3, which then can be combined under one log base 3 while dividing the two arguments together. But remember, the first one goes on top and the second one goes on the bottom. So here I foiled this out. So if you do x plus 4 times x plus 4, x plus 4 times x plus 4, you're going to get x squared plus 8x plus 16. So this part's going to go on top, the 9 is going to go on the bottom, and we're going to set that equal to 2. So now that I have a log with a base and an argument and a value on the right, I can use that formula where I say 3 raised to the second power is equal to this. So there we go. Notice we have 9 is equal to x squared plus 8x plus 16 all over 9. I want to get that 9 out of the denominator here, so I can multiply both sides by 9. So 9 times 9 over here is going to be 81. Multiply this side by 9, it'll just cancel out that denominator, leaving me 81 is equal to x squared plus 8x plus 16. And again, we are down to a quadratic. So subtract the 81 from both sides, kind of flip things around, and we need to find two numbers that multiply together to give us a negative 65, and to add together to give us a positive 8. And that's going to be 13 and negative 5, because 13 times negative 5 is equal to negative 65, and 13 plus a negative 5 is equal to positive 8. That means we have the solutions of negative 13 and 5, which hopefully your little bells are going off saying, oh wait, don't we need to check these? Yes, we do. Starting with the negative 13, if we put it into this logarithm argument right here. That's going to give us negative 13 plus 4, which is negative 9. We cannot have a negative number in the argument, so negative 13 is not a solution. We don't have to worry about it over here because there's no variable. And the 5 plus 4 is 9. That does work, so that will be the only solution here. All right, now let's move on to the next. And now we're going to see how can we exponentiate both sides of an equation. How do we exponentiate both sides of an equation? Well, what does that even mean? Well, let's take a look at an example here. So here I have the natural log of x minus 3 is equal to 5. Now, I could do the formula and say, remember, natural log is just log base e. So I could say e raised to the 5th power is equal to x minus 3. But here we're going to add another tool to our toolbox. So what we're going to do is we're going to call exponentiating both sides, where we're going to put an e on both sides and take both of the sides of this equality and put them in the exponent position. So it's going to look like this. So this is going to be e to this side, where this is in the exponent position, is equal to e to this side in the exponent position. Again, this is called exponentiating. It's something that we can do, just like we can multiply both sides by the same number, or we can add the same number to both sides and keep all of our variable values the same. We can also exponentiate both sides. And the reason that we're doing that, as we talked about earlier, that e and natural log are inverse functions of each other, therefore they cancel out, just leaving what's left there. So when we do that, we're just going to get the x minus 3 over here is equal to e to the 5th, which is what we would have gotten if we had done it the other way as well. And then we can just solve, add 3 to both sides, and we're going to x is equal to e to the 5th plus 3, which is approximately, looks like 151.413 rounded. All right. Now let's take a look. Instead of exponentiating both sides, we're going to kind of do the inverse of that. We're going to take the natural log of both sides. Now this is a great tool when we see an e and we want to get rid of the e. Let me go quickly back to the last one and say, when would we exponentiate both sides? Well, when we have a natural log, that's a good time, because exponentiating means that we're going to end up getting that cancellation between the e and the natural log. So just like that, just kind of looking at it from the opposite point of view, if we have 3 to the x is equal to 14, we can take the natural log. So in this case, we didn't have an e, so yeah, that's not going to matter in this specific situation, but we can still take, just like we can exponentiate both sides, we can take a log of both sides. Now remember, natural log is just log base e, so we can take the natural log of both sides. And the reason that we're going to do it here is because we have a variable in the exponent position. And when we have a variable in the exponent position, it's normally hard to get that variable out. But since we know logarithms, we can take that exponent of our argument and bring it out front under multiplication by taking the log, any log of both sides. In this case, I'm just doing the natural log. I can then take the variable of x and bring it out front under multiplication. Therefore, all I have to do is divide both sides by the natural log of 3 to solve for x, and in this case, I'll get x is equal to natural log of 14 divided by the natural log of 3. And if we want to use our calculator to estimate that, we can. So we can say natural log of 14 divided by natural log of 3, and we would get approximately 2.402. All right. Okay, so let's take a look at this problem here. Here we have 2 times 3 raised to the 2x is equal to 10. So the parentheses indicate that this 2 is on the outside as a factor, right? So we're not, this exponent of 2x is only being applied to the base 3, not to the 2 out here. So the first thing we would want to do is get rid of this 2. And the easiest way to do that is just divide both sides by 2. So if we do that, 10 divided by 2 is going to be 5, so we'll just get 3 to the 2x is equal to 5. Now, again, we have that variable in the exponent position, so taking a log of both sides is a good idea. Again, I use natural log. Why did I use natural log? Because it's an easy key to hit on my calculator. If you'll notice that log button right here. I also have the natural log here. I also have the log button there. So both of those are great log bases to use because they're just sitting right there on our calculator. And we'll get the same answer regardless of which one we use. And I'll actually show you that in this problem here. So once we take the natural log of both sides, that's going to allow us to take the exponent and bring it out front under multiplication, just like we did right here. And then we can divide. Notice that it's just not a natural log of 3. We have a 2 times the natural log of 3. So, well, first we can divide both sides by natural log of 3. And then I can divide both sides by 2. Or in this case, I just kind of multiplied each side by 1/2. That puts the 2 down here. And if we go to our calculator and we do natural log of 5 divided by, and put the entire bottom in parentheses, 2 times the natural log of 3, close parentheses, and we're going to get 0.7325 approximately. Now let's just try with a regular log. Even if we just used a regular log, we should end up getting the same answer here. So divided, remember this is a log base 10, so 2 log of 3, and if I did that right, we'll get the same answer as before. So again, we can take any log of both sides as long as we do the same on both sides. All right, solving exponential equations. Well, here we have 0.9 raised to the x is equal to 10.1 raised to the negative x. So let's see, how would you go about solving that? Well, again, we have the variable of x in the exponent position. And in fact, we have it in the exponent position on both sides. So taking a log of both sides seems like the correct method to use here, although there's other methods that would work. So again, I just did natural log out of ease of use. And once I do that, then I can take those exponents and bring them out front under multiplication. So I have x times natural log of 0.9 is equal to negative x times the natural log of 10.1. So now I'm going to add this part here to both sides, the right side, the negative x times natural log of 10.1, in order to get an equation equal to 0. And from here, I have the common factor of x, so I can factor that out. And then finally, I can divide both sides by this huge value here, the natural log of 0.9 plus the natural log of 10.1. But in this case, it's not really important to calculate that. Why? Because we're just dividing 0 by it. We know that the logs of values are always positive, so this is a positive number plus a positive number, which is some positive number. Hold on just a moment. Excuse me, that was a quick error there. So the whole natural log is not always going to be positive, but we know that the argument here is always going to be positive. And so here, the natural log of 0.9 is actually going to give us a negative value. But still, if we add these two together and then we divide 0 by it, we're just going to end up getting 0. So 0 is our solution. And if we're not quite sure about it, this is where I might go to our friendly graph Desmos, like right here, and graph both functions, and we will see that both of them meet right here at x equals 0 and y equals 1. Let's see if I can do that a little bit. There you go. Okay. Moving on. This one is going to be a bit trickier, and I do not expect anyone to get this on the first try. So if you want to challenge yourself and give this a try, you can, but this is using really some more advanced types of exponential rules and substitution. So here we have a function. We have 2 raised to the 2x plus 2 raised to the x plus 1 minus 48 is equal to 0. It's not easy to see, but this kind of looks like a quadratic, right? And if we can find something that we can substitute for a variable and turn it into a quadratic, that's what we want to do. So again, I wouldn't have seen this until I had done a few problems like this, but here it looks like if I can do a little manipulation, I can kind of get a 2 raised to the x in these first 2 terms and treat that as my variable. So in order to do that, remember kind of the reverse of what we did earlier. If we have an exponent, we can, with the 2 values in the exponent being multiplied together, we can change that as 1 to the exponent of the other. Because remember, if you take an exponent and you raise it to an exponent, you can combine them under multiplication, so therefore you can do the opposite. So for this first one, I'm going to rewrite this as 2 to the x squared, because I see this 2 to the x and I want to treat that as just like a variable. And again, if you were to multiply both of these, you would get the original back. It kind of shows that would work. And here we have a 2 to the x plus 1. If we multiply 2 of the same bases together, we can combine it under the 1 base where we add the exponents. So here's 2 to the 1 times 2 to the x. So if I were to multiply these 2 together, I'd get 2 to the 1 plus x, or in this case 2 to the x plus 1. So just like I can combine them under 1, I can also separate them under 2 like this. And I'm doing that because, again, I get something that looks like my variable 2 to the x, and then I have minus 48. So if I were to let 2 raised to the x power just be another variable like t or s or anything, this is going to look just like a quadratic equation. So that's what I'm going to do. I'll use the variable u. There's no specific reason I used u. And I'm going to let u equal to 2 to the x. And if I do that, wherever I see a 2 raised to the x, I'm going to replace that with u. So I'm going to have u squared plus 2 times u minus 48 is equal to 0. Now we have a nice quadratic function that we can solve. So again, we're looking for 2 numbers that multiply together to give us a negative 48 and add together to give us a positive 2. With a few checks, that's going to be pretty easy. It's going to be a positive 8 and a negative 6. So we can factor that as u plus 8 times u minus 6, where I'm going to get u is equal to negative 8 and 6. Now here's the deal. We have this in terms of u, but that's not going to be our final answer because we made a substitution earlier. So since we made a substitution, now we have to substitute back. So now I'm going to go back to my u is equal to 2 to the x, and I'm going to replace u with a negative 8, and then I'm going to do it with a positive 6, and I'm going to solve for x for both of those, so I can get that in terms of x. So again, I'm going to do, for the negative 8, I'm going to do 2 raised to the x is equal to negative 8. Just replace the u with that negative 8. And we have no solution. Why? Because 2 raised to the x power is always going to be a positive number. It's always going to be a positive number. And let's see why. Well, if we let x be a positive number here, let's say 5, 2 to the 5th, no matter what positive number, we can see that you're raising a positive number to some positive power, and you're going to get a positive value back. If I let x equal 0, well, 2 to the 0 is just 1. That's still positive. And if I let x be negative, like a negative 3, remember, we can change that exponent from negative to positive by taking the reciprocal of it. So if I had 2 to the negative 3, that would be the same as 1 over 2 raised to the positive 3 power, which again is going to end up being positive. So this will have no solution here. We can see that if we wanted to graph that as well. So negative 8 here, we can kind of just leave alone. Let's try the 6. If I do 2x raised to the 6, again, we have x in the exponent position here. So I can take a log of both sides. Again, I'm going to do natural log. That way I can bring the x out front and then divide both sides by the natural log of 2. And I'll end up getting natural log of 6 divided by natural log of 2. And that's approximately 1.099. All right, I know this has been a long video with a lot of things to go through. Please try some problems in the MyMathLab homework. If you have any questions, let me know, and I hope you all have a great rest of your week. Thank you.